Hello and welcome. I am pleased to have you join us today for a webinar on cavitation, uplift, and drainage issues. Today's webinar is the third and final webinar in a series organized by Alberta Agriculture and Irrigation in partnership with the Canadian Dam Association. I am Jenna Montgomery, Chair of the CDA's Professional Development Committee and a manager with Alberta Agriculture and Irrigation. I'm coming to you from Edmonton, Alberta, and Treaty 6 territory, the traditional lands of the Cree, Métis, Dene, Blackfoot, Saulteaux, and Nakota Sioux. I also now call these lands home and share in the knowledge of the people who have known this place for millennia. A poll's going to come up on the screen, and we're just curious to see where everyone's coming from today. As you use that poll, let me introduce you to the Canadian Dam Association. The CDA is a national not-for-profit organization for the advancement of dam safety principles and practices. It relies upon members from all sectors of the dam industry to carry the CDA's vision and mission. Membership is open to individuals and corporate groups and must be renewed annually. Student memberships are also available, and please visit the CDA website for more information. CDA members collaborate to develop guidance and best practices, such as the dam safety guidelines. Volunteers also develop, plan, and deliver workshops, webinars, and the annual conference. There are always opportunities to volunteer, and please contact the CDA for more information. One of the benefits of membership is full access to all webinar recordings, but for this Alberta Agriculture and Irrigation series only, limited time access will be available via the Alberta Dam Safety Events, Seminars, and Workshops webpage, and the web address is on the screen. Please note that your feedback on today's webinar is very important to the CDA, and please check your email for a short survey. Before we introduce you to our presenters, I'd like to draw your attention to the disclaimer on the screen. Today's webinar is not CDA guidance, and that any views or statements expressed are those of the presenters. I'd also like to draw your attention to the Q&A function at the bottom of the Zoom window. Please use this to submit any of your questions. We'll have 3 Q&A sessions kind of scattered throughout the presentation today. There may also be written responses to your questions, so do check back into that function throughout. I would now like to pass things over to Mohan Acharya. Mohan is a senior dam safety engineer with Alberta Agriculture and Irrigation and represents Alberta on the CDA's board of directors. Mohan.
Thank you, Jenna. On behalf of Alberta Agriculture and Irrigation, it is my great pleasure to introduce today's speakers on cavitation, uplift, and drainage issues for hydraulic structures. Today, we have 5 subject matter experts from Tetra Tech, Canada, discussing various aspects of this topic. Daniel Johnson, Principal Dam and Hydropower Engineer with over 50 years of experience, has been a project manager and technical lead for over 200 projects around the world. Daniel, a respected educator and investigation, design, and construction, has active technical leadership role in many agencies such as ASDSO, USSD, and ICOL. Today, Daniel will help us understand how the cavitation, uplift, and drainage issues are managed and lessons learned are implemented using some case studies on some dams with failure to near failure of spillways. Our next 2 speakers, David Massini and Chiranjeev Khanjilal, will be using some local examples of projects to discuss the methods of assessment and evaluation of spillway under drainage system in relation to common failure modes and quantification of risks. David has over 20 years of broad range of experience in hydraulic engineering, including spillway hydraulics, emergency spillways, and low-level outlets. Similarly, Chiranjeev is specialized in numerical modeling, computational fluid dynamics, and many other areas of hydraulic modeling and analysis. Dr. Božena Černovský has over 35 years of experience in research, product development, and consulting in Portland cement technology. Her research interests include Portland cement mineralogy, durability, forensic analysis, and the impact on service life predictions. She will be providing an introduction to grout and concrete in dam construction and the impact of grouting under reservoir head and the risk of uplift and associated concrete failures. And our first speaker today, Dan Hajdakovic, has over 35 years of experience in hydrotechnical engineering. Dan has a PhD in water resource management from the University of Belgrade and is currently a senior water resource engineer. Today, Dan will discuss the fundamentals of cavitation, uplift, and under a slab drainage system and their roles in enhancing the integrity of hydraulic structures. Dan's talk will essentially set the stage for the next 2 hours. With that, take it away, Dan.
Thank you for that introduction. Basically, we will start our sharing now. I hope you can see the screen.
Yes.
Yes, Dan Hajdakovic is my name, and I'll be talking about some fundamentals of cavitation, uplift, and drainage, related drainage to, in general, structures that are subjected to water head and water flow, in particular dams and especially spillway chute slabs. Cavitation, we're starting with cavitation because it does start with cavitation and the process that we, in the end, can damage our structures. What is cavitation? Cavitation is a process of formation of a gaseous phase of water, vapor or steam, when it's subjected to reduced pressures at constant ambient temperature. So basically, I'll draw your attention to the graph on the side, on the right side, where we do have a relationship between temperature and pressure exerted on a body of water. Water, as we know, is what we call a Newtonian fluid. That means water cannot be compressed or stretched, as opposed to, say, gaseous substances at normal temperatures. As a consequence of that, when water is solid below 0 degrees temperature, it is in form of ice. But if the temperature is higher than 0, basically water retains a characteristic that it can be both in liquid or in steam phase, depending on the pressure exerted on it and the temperature. For example, if we are talking about ambient temperature at 20 degrees Celsius, there is a possibility for water to actually enter the steam phase, the gaseous phase, and it depends on the pressure exerted on that water. The relationship between those two is best presented with a Bernoulli equation, which is the equation down to the left. And it actually tells us how the movement of the water and the location, hydrostatic pressure, movement, and the actual pressure within the water body, how they are related. Their sum is always constant. And everything else being equal, for example, for our facilities, dams, and spillway, the hydrostatic pressure is irrelevant. When we talk about the movement of the water, especially over spillways, the increase in velocity squared is inversely related to the pressure within that body of water. Come back to the diagram. Basically, when we increase the velocity, the pressure will drop. And if the pressure drops below this line, water will enter the gaseous phase. We call that cavitation. Basically, the small droplets of water within the body of that water will bubble up. And that's what's called cavitation. I'll draw your attention to the red square here, or red rectangle. We're showing the velocities of water in certain situations. In this case, it is the situation where we have an offset in the bottom of the channel where the water is flowing from left to right. At the beginning, before that offset, we have a uniform velocity or average velocity in that stream of water. However, when we are closing to the offset, the picture, the actual distribution of water velocity across the depth of its body will change, and velocity immediately downstream of the offset will increase substantially. Remember, the square of velocity will make this change even worse, even larger. So the pressure will drop substantially. And that's what happens in this eddy immediately downstream of the offset. Let's imagine that this is a spillway chute, and we have two slabs that are not really joining at the joint. The situation will immediately switch to cavitation situation. And depending on the change of velocity here, we will have either no cavitation, when we are lucky that the velocity that didn't change that much. We have a start or incipient cavitation, where only a few bubbles of vapor happen due to fairly or relatively low change in pressure. We can have a developed cavitation where many small bubbles happen, but they are still, we call that a swarm of bubbles. They are not joined together. And then in supercavitation, all that vapor happening due to cavitation actually join together and produce large cavities in the flow. Why is that important? So basically, that's why cavitation happens in the first place. The problem with the cavitation is that it's very temporary. The bubble forms, and immediately due to the rest of the water body pressure exerting that pressure to it, it'll collapse on itself. When collapsing, it happens extremely quickly and extremely intense collapse of the vapor void, and that collapse is directed straight downward to the bottom of the chute in this case. You can see on the right a little bit clearer that collapse produces what we call a vapor pick that strikes the bottom of the chute, and the force is enormous. No concrete can withstand that, and even steel is dented with this because it's basically a shock wave of super speed of the actual process of collapse of the bubble. Then, when collapse happens, the local velocity around that collapse increases again. So basically, it feeds on itself. It produces another drop in pressure and another bubble in the water flow. So the process continues as long as the shock wave makes enough velocity change for water to evaporate. So this is on the scale of a single bubble, but usually, especially in developed and super cavitation situations, those bubbles group together in swarms or even create large cavities, voids in water. And they cumulatively exert a huge force on the bottom of the structure. That's why we have damage to the structure, because it is like a jackhammer on steroids. It starts chipping off the surface of the boundary. This is how it looks and where it happens. It happens in both offset into and away from flow. Those are the first two examples. It also happens on the curvature away from the flow. Usually what happens in even in well-built spillway tubes. Also on a abrupt slope away from the flow, damage happens immediately downstream of the change of surface. And then I'll draw attention to you that of the case F, roughened surface. So basically, even if we don't have any change in any offset in hard surface, in this case, shoot slabs, even when the surface is roughened due to, say, ice cycle in the flow, and basically the surface damaged and roughened by the weathering of the material, we will have cavitation happening and damage to it. That's very important because we need to know when it happens that we know it will happen. This is the example of the spillway chute where we have the advanced cavitation eroding the spillway chutes. And that's happening even on a structure that more or less has a sound design of the joint between the two slabs. Two slabs have to be built separately because that's how we build chutes. It would be ideal if it were all cast in one place, but that's practically impossible. And also, if you remember the previous slide, even in solid and continuous structures, due to some other issues, we can have a roughened structure and cavitation will happen regardless. So in this case, the slabs were joined properly with rebars and dowels across the joint. So to prevent the differential settlement between the two slabs. However, cavitation happened due to roughened surface and the mere existence of the joint. So the cavitation eroded a lot of concrete all the way down to the rebars and all the way down to the water stop, as you can see here. So this is my last slide on cavitation, showing what can happen first. We have erosion of a concrete slab to the extent that now we have an opening that will allow access of water underneath the slab. So in that time, the process of uplift on the slab due to just access of water underneath it will happen. So now it's time to talk about the uplift. The uplift pressure or hydrostatic uplift, it's upward force applied to structure that's submerged in water. It is first studied on gravity dams, concrete gravity dams, which I have on the right. And basically, it is due to the pore pressure happening underneath the structure and forcing buoying the structure upwards. We have no drainage on this structure, so this is a natural condition in a good foundation of the dam. The uplift will have this form because at the upstream end it will be equal to the hydrostatic pressure exerting at the upstream face of the dam, and the bottom the same from the downstream side. The straight line tells us that the pressure is dropping due to the hydrostatic drop across the foundation of the dam. That's not always the case, and we will see that on the next slide. However, the force exerted on the structure is equal to the area that this trapezoid diagram has and exerts towards the structure. So here I have a few examples what happens. The left is the same from the previous slide. The middle one is when we introduce drainage to the foundation area between the heel and toe of the dam. And if the drainage is done properly, we will reduce, because we remove the water that exerts that pressure on the structure. We remove it and convey it away, usually downstream of the structure, and by that we are reducing the pressure on the structure. However, if the structure itself or the substrate, the sub layers in the foundation of the dam are cracked, they will be subject to the full pressure or hydrostatic pressure upstream of the face, and the diagram will look like this, the red line. So with bad drainage or the drainage not properly applied to certain areas of contact between the structure and the bedding material, we can increase the pressure and increase the force on that structure. And it is known to topple the dams. Imagine what will happen to a rather relatively thin structure of a spillway slab, which is there not working by the weight of its own weight, but basically it works by connection to the other slabs in the structure. So to the left, we can see what Uplift can do, move extremely large blocks of gravity, very heavy concrete material. And if it can move structures like this, it is not a surprise that when water enters the cavity underneath, even if the drainage is done properly before the cavitation actually opens the holes in the slab, when the water enters the holes underneath the slabs, it can easily lift them. And then after that is all erosion and forceful removal of the slabs and substrate material. So on this diagram here, and I think it's a little bit clearly more shown to the right, it's the same diagram. We're showing all the forces that are exerted on a joint between the two slabs. So we have cavitation that works from the top, uplift that works from the bottom in the upward direction, I-cycle that makes the whole process worse because basically it will erode concrete even more, especially when it's cracked or it has voids inside. And water flow forces, because now water, because of the offset in the slabs due to the uplift and cavitation, will now expose the upstream lip of the slab water forces of the flow. How do we prevent this? First, we have to prevent two issues: cavitation from the top, and with drainage, prevent the uplift pressure on the slab even before the joint is offset. And the proper drainage, which my colleagues Chiranjeev and David will talk a little bit more later, will prevent the uplift, and by that, indirectly, reduce horizontal forces on the slab due to the force of flow, and reduce further cavitation damage because the offset will exacerbate the process of cavitation at the top. We on this picture now can show what is the end game here. The cavitation started at the joint here between the slabs, damaged it even more so because the drainage, and David will talk about that, drainage of this site, it's Orville Dam in the States, was not properly done. So we damaged the first slab, and then from there, it's all downhill. The first erosion and removal of the slab will aggravate the situation even more, and in the end, the sheer flow of water will erode the foundation and remove the rest of the structure. So this is the end for my presentation. Chiranjeev and David will talk a little bit more about the actual practical issues with design of the drainage underneath and around the structures. But this is the time to actually hear some questions if there are any.
Yes, we've got a couple of questions, and I'll just remind everyone, please use the Q&A function at the bottom of the Zoom window to submit any questions. So our first question, in the fundamentals of cavitation, is the shockwave only sent in a downward direction towards the slab, or is it sent out in all directions?
It is sent out in all directions. However, the shockwave, same as sonic boom with planes, will move with the cavity. So, and water is the propellant of that move. So water will flow downstream, and the shockwave will mostly be felt downstream of the offset.
And here's another question about the shock wave. What is the mechanism that causes the secondary shock wave?
So the initial collapse of a cavity or a bubble produces again a change in velocity. So new bubble shows up, and a secondary shock wave immediately follows. So each collapse produces a new shock wave.
Okay, thank you. Next question, can you develop cavitation around gate guides?
Oh, definitely. It happens wherever water flows, in pumps, turbines, gate lips, anywhere where water flows, especially where water is forced to flow in jets.
Okay, next question. Inspection-wise, are there any key visual indicators of cavitation damage on a spillway to differentiate from, let's say, surface falls caused by ice or poor subgrade?
Initially, no. The initial damage by cavitation looks exactly the same as ice cycle erosion of concrete. However, ice cycle erosion of concrete happens everywhere where temperatures are low. The cavitation usually happens downstream of offsets, joints in this case.
Okay, so there is a question about Oroville Dam. We'll get to that later in the presentation today. That is one of the case studies that will be discussed. Next question. Does cavitation only occur in supercritical flow regimes?
The simple answer is yes. There are fewer exceptions that are not related to a surface flow, free surface flow.
Okay, and another question. So narrow weirs are not subjected to cavitation generally. What situations, or in what situations could cavitation occur on a weir?
Well, I would disagree. It can, but that's not a sound design. However, we've seen it, and if it's not a sound design, it doesn't mean it doesn't happen. It does happen. However, it happens on the lip of a sharp crested weirs, and sometimes we introduce steel bars on the top of the weir in order to prevent damage to it.
Okay, and now there's a question about ways to prevent cavitation, but I think we'll get into that a bit later, correct?
Yes.
Yes.
Yeah, so we'll hold on to that one as well. Yeah, I think.
I can see the question about emerging technologies.
Yeah, okay.
No, this is not rocket science. We have found out, and David will talk about that, the ways to actually prevent cavitation. However, if that's practical to be used, especially on existing structures, that's a different question. I'll leave that to David to explain.
Okay, and we'll just one last question before we proceed with the next section of today's webinar. How would this cavitation process create rock erosions, since there are much more irregularities on the rock surface compared to a concrete slab?
Well, we use supersonic drills on solid rock to drill tunnels, and it works. So basically, it's the same process. We are actually using the same process in order to drill intentionally. So it does happen on rock, solid rock, but it is less frequent in our practice.
All right, thank you. So again, continue using that Q&A function down there, and yeah, take it away on the next part here.
All right. So my name is Demoskini here. I'm here with Chiranjeev Kanjilal. I'll cover in the different methods of assessment and evaluation of aeration and under drainage systems. And Chiranjeev will concentrate on some of the tools that are used to evaluate the performance or the hydraulic performance of spillways. So first thing is, when we look at different spillways, there's different failure modes that we explore and we review. Today, I'll be concentrating on two of them. The first one is cavitation and uplift, which Dan explained the science of. And then I'll take a look at, I'll present about the poor and failing drainage system, things to look for, and how to potentially address some of these issues. So I brought, for this presentation, I looked at some of the examples that are specific to Alberta. The first one here on the left-hand side is the Waterton Dam in Alberta. And as Dan mentioned, typically cavitation issues develop around the joints of the concrete. You can see here, these are cavitation issues being so close to the edge of the joint. They are happening upstream, and as Dan mentioned, although for the most part these issues do happen at the downstream end, depending on the roughness and the geometry of the surface, they can actually migrate also upstream of the joint themselves, right? So that's when you visit a spillway and do your walkthrough, you know, all repairs are signs to look for, right? And then look at the joints and then what's happening around those. Look for differential settlement between the joints themselves as well. The other dam that I'm showing here, this is an old spillway that was eventually abandoned. But you can see here how, you know, this St. Mary's Dam spillway was constructed, and soon after construction, it started to fail in many ways, and there have been many repairs done to it. And you can see at the end, you know, they added a lot of anchor bolts to try to keep the slab down. Now, one thing important to consider is when visiting or inspecting a spillway is, you know, the important thing is to concentrate in areas where you have the greatest change in grades, right? So on the chart that I'm showing here, or figure I'm showing on the right-hand side, you can see how the vacuum distributes across the spillway, right? So the very top there, close to that area, identified as Area A, that's just downstream of that location is where you will see the greatest development of vacuum. And those are the areas that you really need to concentrate on, because that's where the cavitation is likely happening. And those are the areas which are very important to inspect. Now, this is what happened, you know, at St. Mary, Alberta. This is the old spillway on the right-hand side, which eventually it was abandoned because of all the issues. The one on the left-hand side is the new spillway, and I'll highlight some of the details that we've noticed in some of the inspection picture that were provided. One thing to notice right away is the change in the slope, right? The old spillway, very steep. This steepness does not help. It is a lot of energy that the spillway has to handle and translate from the upstream end to the bottom to the downstream end. So trying to you know, reduce and make more gradual changes. I think it's a good design practice. But anyway, so just wanted to show you how a poor design can lead to very expensive solution, all the way to having to reconstruct the entire spillway itself, right? Now, how do you prevent aeration? There's a good textbook, Hydraulics of Dams and Reservoir, that you know, was by Fuats and Turk. It basically highlights the importance of aeration, right? So if you are able to get in about 7 to 8% of air supply in your flow, you're basically able to prevent cavitation. Now, how is that done? There's different examples here on the right-hand side that I've included. There's little ramps that can be added. There are ducts that can be, you know, included in the actual structure itself. Duct under the ramps. All these are options that can be incorporated in the initial design. Now, these are tough to bring into a constructed structure already, but that's what's typically done nowadays to prevent cavitation. Now, as anything, these ducts and corridors that are being added to the structure, they need to be inspected. You need to make sure that these are functioning when they need to operate. In Alberta, for example, where temperatures drop significantly below zero, and where you could have a early freshet. Some of these aeration systems may be completely frozen. And so very, very important to always inspect these and make sure that these are ready for the freshet, for example. Now, there's another textbook that I encourage everyone to read, especially here in Canada. It's a hydraulic structure by C.D. Smith. There's one interesting section. This book was initially written in the 60s, but even back then, there was the discussions about the importance of a proper drainage system. The drainage system is what helps reduce pressure underneath the slabs of your spillway, and also prevent, in some cases, actually acts as an aeration system in where that is possible. But more importantly, it is a tool that allows you to remove the pressure underneath the spillway chute and prevent uplift, for example, right? Now, one thing important to notice is that these under-drain systems need to be constructed properly. Some of the details that I'm showing here include, for example, the addition, beside the construction of the concrete slab and the joint and the water stops, all designed to prevent migration of water into the area below the actual chute itself. It is important, especially in regions, colder regions of the country, to include insulation systems to make sure that these under drains are not frozen, especially during an early freshet when the temperature the ground is still frozen and there is a change on the temperature on the surface. And so you have water now flowing on the surface, but your under drain is completely frozen, right? So these type of insulation systems are very important for that. It is also important to make sure that there is a filters layer around the under drain system, and there's a gravel system also allowing water to migrate into your under drain pipes, right? So all these details are very, very important to make sure that the water that may be present underneath the slab is actually able to migrate out of that area away from the slab and reducing therefore the uplift pressure. There is obviously this anchoring system that are also added to prevent that water from migrating downstream to the next under drain. So it's important to separate these and make sure that these under drains are large enough, they're spaced so that they are sharing the load of water basically underneath. So those are all details that are often overlooked when integrating under drain systems. Now, Alberta Transportation has a very good detail that I included here as an example. And you can see again the insulation system in place, the water stop, filter, the drainage gravel around, fairly large, drainage gravel detail there. The cross wall that goes across, stopping water from migrating downstream to the next one, and the filter sand also, because obviously you have to make sure that your gravel is filter compatible with the soils that are in situ, right? Now, there's more details you can see at the joint. These are, there's a lot of work that needs to go into maintaining the joints. There are joint fillers that are used, especially pavement structures. It's very commonly done, but these systems need to be accessible so it can be removed. You can see there's the top plate can be removed. You can expose the joint. You can remove the joint filler after many years and replace that again, right? So these are things that are needs that need to be maintained and looked after for the duration of the life of the structure. Now, one thing that I really enjoyed reading recently is the independent forensic report that was done for the Oroville Dam. But the first thing that attracted me to that when I started, noticing picture was these jets of water that were coming off the side. And especially here on this picture here, what is interesting to see is that the water actually spilling out from the side is actually higher than the flow itself, suggesting that there's groundwater pressure underneath that is basically emerging out, right? And that in general, not a good thing, right? So that's the first thing that is important to notice. But what I extracted with these two figures out of that report. What is interesting to see is you can see the blue circles there. These are the cross drains that were installed underneath the spillway itself. And then they had these release points collecting all the water coming out of these cross drains and then discharging back into the spillway, which is a good idea in the sense that you're putting the flow back into the spillway itself. The issue, obviously, is that these under drains, when they are spilling through these openings, it suggests that there's quite a bit of pressure already developing underneath the spillway itself. Now, these under drain systems were older, and back when these were installed, it was the technology of the time. They used vitrified clay pipes. Those are, the solution that they had at the time. Nowadays, we wouldn't dare doing that anymore. There are too many joints. The joints don't have gaskets, so they leak. So again, that's not a fault of the design itself. I think the concept was good. The issue is that there was not enough drainage to handle all that water. Now, if we look. Now, if you look at the other, figures that I've extracted from the same report, the under drain system on the left-hand side here, you can see it had collapsed. So vitrified clay pipe is very brittle material. So even during installation itself, these things, it's very easy to break them. And so that's obviously a problem. If your under drains are plugged, they will not work. The other thing too is they were installed underneath the slab, thinning out the actual thickness of the slab. And the issue here that you can see, the area highlighted in red around the under drain, is just not enough area to hydraulically allow the water to migrate from the surface underneath into the under drain system, right? So always very important to make sure you have enough area there to allow that to happen. Now, this is going back to our example in St. Mary. This was the example of, the spillway. You can see on the left-hand side, there was an under drain pipe included. There was gravel, but there's no filter. There's no filter layer. So for all we know, the fines had migrated into the gravel, blocking these under drains. So that's one issue that's common. And then you look at the very bottom, they had installed an under drain system, and the issue they developed there was too much pressure that actually lifted the actual concrete slab. And you can see the area highlighted as D. That was the lift that they noticed, being approximately 4 inches. Why? Because although it was very well built, that under drain system there, because you can see the filtration going through, it probably was not enough to handle all that water that was getting down there, right? Now, this is the new Spillway St. Mary. There are now inspection, chambers or manholes, allowing people to take a look at the under drains, see how much water is getting out. And you can see this is the picture on the right-hand side. This is a very bottom of the system. You can see the under drain on the left-hand side, the green one. There's no marking on the concrete suggesting there's no water down there, which is great. And then the larger one, there is a little bit of seepage, but now having access to the under drain, one can go and inspect and maintain and clean these under drain. So under drain systems are, when they're flowing, it is indication that there is a problem, and one needs to understand why that is and where is that water coming through, right? So I wanted to bring up the water turn down. This is an interesting design that I enjoyed reviewing. you can see the designer from the beginning was trying to keep out the water from underneath the concrete slab. How do we see that? Well, we can see that from the clay cutoff area that we have at the upstream end, extending down below the compact select gravel. Now, the designer included a series of under drain at the bottom end. I would have pushed them into the gravel itself, but we don't have details about how these were constructed, so we'll assume that they were properly built. But at the end of the day, those under drains, if they are active and these are accessible and one can monitor those, when water is flowing through these under drains, one is able to conclude that there's been some migration through the clay cutoff from other areas into that area itself. When water migrates, builds up all the way to the top layer of under drains, which are right underneath the spillway concrete slabs. If you see water up there, then there is a problem, because that means that the entire area underneath the spillway is full of water, right? Now, the issue is, where would I concentrate my attention during the field visit is, again, what we talked about, the transition from the flatter area of the spillway, where it gets steeper. And if those under drains, those 3 under drains that are highlighted in the rectangle highlighted, are flowing full, we're having a problem, right? That's a problem. Now, the other thing too, you don't see too many cutoffs along the spillway, meaning that if these under drains are plugged, there's going to be a buildup of pressure, all the way down to the bottom here. Now, one thing that is important to see, how far apart are these under drains? Do you have enough under drains there to relieve that pressure? Now, one thing also important to notice is that the type of material that's surrounding the spillway, you can see the alluvial material, which is probably free draining, and that material, if you have water, it basically allows water to migrate in and out of this area unless it's contained and controlled, right? So very interesting design, a good design, but it's important, again, be strategic in the way you use these under drain system to allow you to understand what is happening underneath. Make sure they're properly spaced, make sure there's proper gradation, proper gravel filters systems in place. Very, very important tool to understand what is happening underneath your spillway. And with this, I am going to let Chiranjeev cover the CFD modeling and how it is important.
Okay, so the story so far has been the discussion on how cavitation forms, what effects it can have, what it does in terms of wear and damage, and then how it results in other things like uplift. And so with respect to assessments, we can use computational fluid dynamics, CFD, to analyze and take a look at some of these sorts of scenarios. CFD is a powerful tool that solves the equations of motion for fluids. And we can look at simple and complex scenarios. Well-built models can be used to test different designs, different visualized prototypes, conduct sensitivity analyses, test different geometries, flow situations, mitigation, things like that. And in the context of cavitation, we can look at cavitation from water hammer, negative pressures that develop, impinging jets and bubbles, dissolution, air entrainment, and then something else that might be relevant is localized wear. Let's let these run. So with CFD, we can build some sort of system and take a look at the flow patterns that develop, the negative pressures that develop. In the example on the bottom left, I just quickly built a poorly designed spillway, but we can see how the flow travels across the crest, and then a large air pocket appears to develop underneath. There's a lot of flow separation. And if we imagine walls on the ends, on the sides of this channel, that can be an area where cavitation develops, large slugs of air or bubbles. You can imagine a situation where the fluid separation isn't as much, but negative pressures can still develop by the nature of the fast flow. Another example on the bottom right, pause it the right moment, we can see how there are some gaps that appear as on the downstream end of the crest. So we can look at all sorts of scenarios where the cavitation can occur. We can import different geometries representative of the actual spillway, and then look at different flow inputs, flow scenarios, see what happens. One example I'll share here, this is the same spillway as before in the previous example. In the top left, we can see the flow velocities. The scale runs from 15 to 35 meters per second. In the top right, again, the fluid, and this time taking a look at the pressures, we can see the scale running from minus 30K to 70K, positive 70K, gauge pressure. And in this scenario, negative pressures appear. David and Dan talked about how we should look at that crest there's that point upstream of most of the crest itself where the gradient changes the most, where there's that sort of inflection point. And we can see that in the simulation here, there are significant negative pressures developing. And in the bottom two panels, I'm looking at the void space with two different scales. In the void space, effectively the air, I can see where, if I pause it with some good timing, large pockets, large slugs of air develop with negative pressure. So the scales run from essentially below 1 atmosphere. In this sort of a scenario too, you can also look and see, well, if you monitor the flow upstream and then monitor the flow downstream, and if you build the geometry accordingly to account for that loss that causes uplift, you can estimate the amount of uplift that would happen on the downstream slab. In these things, you can also take a look at the flow patterns in terms of the velocity vectors, look closely at where wear might occur, and also take a look at things like turbulent kinetic energy and shear. Oh, just mouse. Let's do that. There we go. David and Dan's talked about step ups and step downs, how these are problematic. We can import this sort of a scenario. In my example on the left, it runs rather fast, but this is essentially a 1 centimeter step down. So CFD allows us to take a look at a very fine scale, at a very small scale, and we can see, the eddies forming in the velocity, and also the pressure. The pressure scale here runs up to 1 atmosphere. So anything that is essentially colorful and not dark red is representative of negative pressures that develop. And in the example on the right, this is essentially the same thing. I've just illustrated the vectors here and shown the step up, but the colors represent the velocity and the disturbance there, and the eddies that can form at the corner, causing those horizontal forces that Dan talked about, and then how cavitation might occur with the velocity change downstream of the step. And with that, I will give it back to David, who has an anecdote for us, I think.
Yeah, so this is an interesting figure I'd included. The junior engineers I work with, they have highlighted the fact that there's a new tool we have available called Copilot that will basically put me out of a job. I assured them that they'll be out of a job long time before I would be, but that said, I decided to explore and how useful this tool is, and I asked basically Copilot to produce or design or draw for me a spillway that could handle cavitation. And this is what it produced. Obviously, I would never design something like this. I think it looks more like a water park, and I'm not sure why the handrails were added at the very top, but That said, I admit that it shows how the importance of aeration within your spillway, and the importance of adding steps to reduce that energy. Now, I think this would look very good for a water park for kids, but again, I don't think I'll be out of a job anytime soon. But
Okay, thank you. Yeah, so we've got somebody saying, do you think we're actually going to be out of jobs with AI?
no,
but I think
no,
that's a whole.
not for now, not for now. As long as the AI adds handrails at the very top of the spill or in the middle of the spillway, I think we'll be okay.
Now, Dan H, there's been a few questions about dealing with or things that can be done to protect from cavitation, but you responded with prevention is the key. Can you talk a little bit more about why we should be focusing on prevention rather than protection?
Well, it's all fine and dandy that we know about the water, but usually the water is quite complicated. For example, the Bernoulli equation works only with huge amount of pre-assumptions. So water is governed by a set of equations that cannot be solved. Saint-Venant equations. Those are used for climate change too, for atmospheric fluid exchange. So basically, understanding the process is less likely to help us from a point of view of prevention, or as compared to the prevention. I think prevention is, especially in our practice, where we want a practical solution that work in a large set of different conditions. Small, I mean, low and high temperature, small and large flows, pressure changes due to the operation of the structure. So prevention, in this case, aeration, is the best way to go. However, we do have to realize that it's some existing structure are difficult to back design or to rehabilitate in a way that it reduces, because the structures are huge. I think that's why we have the example, David's example, that we had to replace the chute completely, the spillway. We built a new one in his example. That's my stand on it.
Right, thank you. There's also been quite a bit of interest in Oroville and the causes of that spillway failure. Now, you did mention that, it wasn't the cavitation, but it was a drainage issue. And there was a question about, would it be, if there was larger diameter drains, would that have solved the problem?
Yeah, so I answered that one. The size of the under drains is not enough, right? The under drains typically, and I don't know if people have seen those up close, but typically there's a pipe and there's perforation that run along the bottom of the pipe itself, right? And you can specify different perforation geometries, and but the migration of water from the surrounding ground into the pipe, it's a very complex hydraulics exercise because you're going through the filter, through the gravel, and into the pipe itself through the perforations. So the size of the pipe, typically, if you have proper gravel system in place and the filter, your under drains needs to obviously be sized to match that hydraulic conductivity that develops through that media, right? Now, in certain cases, it could very well be that in the case of Oroville, they could have they would have needed larger under drains. But when I responded to the question here, I wanted to highlight the fact that just adding larger pipes will not necessarily address the problem, right? It is very important to have the proper hydraulic conductivity to get the water into the pipe in the first place. You can have a very large pipe and the water just not getting in there fast enough to reduce the pore water pressure around the system itself. Hope that makes sense. I saw a thumbs up.
Now there's a question here, and it looks like Dan, you're typing a message.
Yes.
So someone was asking about, okay, so there was an earlier slide, spoke of purposely, whoop, now I lost the question.
Oh, sorry, I
Creating
answered
air
it, so-
bubbles to prevent cavitation. And they asked, can you speak more about that and methods to add the air, current applications? And so, yeah, maybe we can speak to the group about that.
Can we go back to the slide where the air entrainment, David slide, examples? No, down.
Okay, so we're not seeing the slides change here.
Yeah.
Oh, there we go. Okay.
There it is.
Yeah, so these are examples, right? So again, what you want to try to achieve is around 7 to 8% air supply, and that will prevent cavitation, right? So the way to do it is within this. These are little cross sections along the spillway. There's different tricks that are typically embedded in the design in the first place. These are very difficult to bring into a design after the fact or build them after the fact. But if you look at here, these are all basically changes in elevation and aeration system that come in from the side, allowing air to come in into the flow. As the water moves across the spillway, it creates a vacuum. That's what it wants to do. That's the cavitation that we're talking about. There's a vacuum that develops. And if you can break the vacuum by allowing air into that system, you're effectively preventing that cavitation from the vacuum from forming in the first place, right? And if you prevent that, then you don't have cavitation. You don't have, you're protecting basically your structure. Now, where do you put these? Again, where you look at the chart that I presented earlier, there are different locations where the vacuum is greatest. So it's right at the top where you have the transition from, where you have the greatest changing rate, basically. Those are the areas where you want to introduce air, and that will help basically prevent cavitation, right? So that chart, that figure that I have in there, at point A, that would be ideally where you put your aeration system, right?
In addition to that, air serves as a cushion within a water body because air is compressible. So to the shock waves. Shock waves are in all practicality removed if you have air at atmospheric pressure introduced into the flow.
All right, thank you. And one last question before we continue moving along here. Can you discuss the merits and challenges of defining anticipated real world performance and extent of cavitation using either CFD or physical models? They both have their advantages and disadvantages. Any thoughts as to which method is preferred over another?
I didn't really talk about this much, I guess, but let me just read the question at the same time. Oh, it's not.
Oh, sorry.
I guess it sounds like essentially CFD versus, or any sort of software versus a physical model. Ideally, so you can have use models like CFD. The advantage there is you don't always need a physical model to accompany it if you can validate the system. So if you have an existing spillway, if you can validate the flow conditions for how it normally has historically operated, then the model is, you can have a high level of confidence in the model, and you can assume it's going to be quite reliable if it's replicating those conditions. And then you don't need the physical model because the model is validated to the system. Any changes that you make should be representative of what you should see. So ideally, when you work with software, you do have some sort of validation process. And that can mean a physical model, or it can mean the system that already exists, in which case, yeah, you validate against how it has been operating in its existing nature. I didn't get to read the question, so I hope that answered it. But feel free to ask it again, and I can look at it in the chat.
Great, thank you. And I guess we'll move along. Rosanna, I think you're up next.
Okay, I've just answered the prompts here. So we had the fundamentals of cavitation and uplift, and the cavitation affects the top of the slab, and then the uplift affects the bottom of the slab. And then, of course, there are drainage issues that was all discussed, and this is how I want to tie my concrete and grout to the presentation. Because ultimately, all these failures, whether it's the faulty design or change of conditions or anything else, result in materials failure. So this is your concrete. That could be your grout. There could be the construction issues. This is why I'll be talking simultaneously about concrete and the grout and new construction and old construction, because especially in new construction, a selection of material and construction practices can make it or break it. We can design to the best of our knowledge, but ultimately, if material fails, it's a failure. Now, I'll quickly touch on concrete material selection. There are a lot of things. There are CSA standards. There are structural considerations where the main consideration is compressive strength. And then there are also environmental considerations when we look at durability, such as high sulfate content in the soil, alkali aggregate reactions in rocks, but also climatic conditions, and especially freeze-thaw that can affect the surface quality on top of roughing from the cavitation. And then, of course, there are placement requirements, such as it's reinforced, so flow around the steel reinforcement, maximum aggregate size selection, and concrete consolidation, very important. And what is even more important is how do we construct the joints. We cannot construct anything in one simple pour. So when previous speakers were talking about the failures, they usually happen in the area of joints. So this is concrete side, and grout this is a very proven methodology for installing up gradient and down gradient in down foundation, and these are grout curtains. Typically used when the rock formation below of the existing or new dam is pervious and seepage is expected. So this is the way of limit the seepage. Basically, it's somewhat designed the spacing between the drilled holes that are filled with grout to form what we assume is a continuous curtaining the foundation. And of course, if seepage passes through the curtain, it is collected or assumed to be collected by a row of drainage holes. So everything is perfect, minus the fact that when it comes to concrete, we get to see it. When it comes to grout, we actually don't. So we make the assumption that when we design it and it's properly placed, it actually satisfies the function it was designed for. Sometimes we find out the hard way. The best way for grout mix design, we should be very clear in our specifications. Grout properties, cube strength is only one of them. Flow and grout take, erosion versus effective pressure, bleeding, and the selection of admixtures. And the admixtures play a huge role other than Portland cement and super plasticizers, especially viscosity modifier, how to keep grout properties stable. And there is always another requirement of bleed 2% or less. This is the most common. And again, water cement ratio selected mostly for strength. But we also have to play with apparent viscosity and gel time determined by the mix design and the dilution equipment. And then it comes to actual delivery, meaning how do we select equipment to deliver on that? And how do we make sure that we can only go by volumes? So we have to have an idea in our design of the curtain as to what volume is expected. Are we looking at the refusal? Are we looking at seeping grout elsewhere? There are different methods of dealing with curtains. And then, of course, on the completion of that, we have the package that tells us this is how much grout went, this is what pressure formed, etc., etc. And then I'm sort of circulating back to concrete because an important part is how do we form it? How do we have uniform concrete batching for slump and air so we get consistent properties? How do we make sure that concrete cover over steel reinforcement is what it's supposed to be? Because if it's less, we are basically accelerating corrosion of the steel and another type of failure. And then there is placing of concrete. There are ways, especially to construct the spillways. Then comes concrete protection and curing. Again, it can make or break our concrete surfaces. And then we are going back to grout. The same thing that we are asking for uniform concrete batching, we also have to ask for grout mixing and pumping, because for both concrete and grout, whether it's a new construction or a repair, the consistency is the key. Now, I have few examples here. This is unfortunately new construction. And on the surface of it, it's a forming issue and misalignment. And you can see here, do you think that this is a potential candidate for seepage or water going under the spillway? Of course it is. Do you think that this is a little bit of issue? The problem with this is that we try to seal the joints, but it's almost impossible to seal something like this. Well, there are attempts, but this is the first failure, and this is for new construction happening here. Similarly here, when we place the concrete and we get something that is a cold joint, we really don't know whether it's only on the surface or whether it goes deep enough to cause some problems. If we have something like this in a spillway, and this is right close to the joint between concrete panels, and then we have cavitation problem on top of that, that is going to be an accelerated failure. Similarly here, when the actual bottom of the spillway is constructed, this is going to be yet another issue. So we have to be very careful. The design is one thing, but the actual delivery of the materials construction is another important issue. Similarly here, it's a big issue. You really don't know whether this is only what's on the surface right against the form, like here, or whether there is actually a deeper issue and the whole structure is affected by honeycombing. This is how it's being called. Now, so we see it in new construction, and that obviously would accelerate the damage due to all the issues that were discussed by previous speakers. And then we have the old construction where we deal with what to do next. Sometimes it's the upgrade of the design. Sometimes it's just to deal with the basic repairs. Usually it starts with visual inspection of dam concrete elements, identification of what are the issues, whether it's durability or compressive strength. That goes through a targeted coring program. You have to select the locations that will not impact future dam operation. You test for compressive strength and petrographic examination. I don't want to dwell on that too much because all these will ultimately define how the recommendations for concrete condition and repairs are going to happen. And like I said, I want to separate it from the design issues. This is strictly materials, but at the end of the day, it's the materials that are failing. And that goes back to what was discussed before. This is prevention versus protection. And we would rather prefer to be in the preventative side of it. This is one of the examples. It looks ugly, but not necessarily concrete failure, but the cover was inadequate. And of course, with all the exposure to moisture, etc., that would corrode and eventually result in the delamination of the surface. Similarly here, if we are talking about cavitation, these would be the prime targets or where it would develop. These are called joints. And again, the concern is, do they go just on the surface or does it happen exactly throughout the slab, which is a totally different issue and a much bigger concern? Surface repairs in this case do not really help to solve the issue. Here is an example of examination, of course. Sometimes the concrete is cracked, sometimes there is a rebar. By the way, this is not real corrosion, that rebar is in good condition. And then we get to the life cycle of dam structures. They are designed for 75, 100 years plus. And sometimes the analysis of the older dam structures shows that the rehab could extend the service life, and this is the purpose. Upgrade to the current code, extend the service life. The rehabilitation works are very dependent on the durability damage, if there is anything, expected life cycle extension versus cost of upgrades. And of course, grouting operations, again, that go beyond concrete repairs, basically to reduce the water loss. And like I said, this is only materials section, even though the design shows that what fails is the actual materials. Yep. So now I am passing it back to Dan.
And getting loaded. Should be there, yes, right?
Yep, we can see the presentation. We can't see you.
Okay, can't see me. All right, let me. Camera's on. No, it's been off. Okay. Now I hear.
There we go.
Hi, I'm Dan. I'm another Dan 2, I guess here. Anyway, appreciate kind of coming through here and listening to what's going on with all these presentations. A lot's happening. I'm going to talk a bit about some case studies and looking at what happens and what can be done. And so that's part of it. And as talked about, like David did and others, about inspections, really important. And just a quick plug for CFD analyses. And in this graphic, up the upper left-hand corner, this is a spillway that's flowing during a flood. And if you look at the upper left side of that spillway channel, you can see that the water is actually at the top of the channel. And then the result is the lower photograph. So the spillway capacity was fine. The channel capacity was inadequate. And that's something we don't always look at, but I think it's an important point. And with CFD being so efficient these days, it's a good way to look at spillways, not just with what the deterioration is, what the capacities are. And let's go on. Okay. So I'm going to start talking a bit about Oroville Dam that was discussed a bit earlier. And of course, I think it's worldwide of what's happened with Oroville Dam. As far as I'm concerned, it's one of the giants of the near failure. As we know, the dam did not fail. The spillway, both the service and the emergency spillway did fail. But it's a big project. It's been around for 50 years. It was built in the 60s and 70s. It's a 213 meter high zoned embankment dam. The reservoir has 4 billion cubic meters of storage. There are 2 spillways, and the capacities of the 2 are about 11,000 cubic. So it's a big project. The operating spillway, which is the one that failed initially, has a capacity of 7,000 CFS CMS. QMAX, and then it's got a gated crest. You can see in this photograph, the chute is long. It's a kilometer-long chute. The upper portion of it's relatively flat. The lower portion is kind of a uniform grade that goes all the way down with a curved transition from one to the next. And at the base is stilling with a flip bucket and stilling basins down at the bottom. This photograph is actually taken during the runoff when things were a problem and started to flow. Emergency spillway was to the right of the dam and the operating spillway, and this is the post erosion photograph of that. But you can see the operating spillway at the top of the photograph, and then the emergency spillway is the concrete structure there. You see extending from the right of that gated spillway. It has a design flow of 4,000 cumex. It was an OG crest. It has an apron of concrete, but you can see a little bit left of it. But then from the apron down to the river channel, it was just on the natural soils and bedrock. And the understanding was that the bedrock is sufficient to handle the very rare opportunity for an emergency operation of that spillway. That flood event that occurred was kind of a bit of a problem for everybody. They had excellent snowpack. It was a wonderful year from the Sierras, and they had a warm spring, so runoff happened very quickly. The reservoir filled very quickly and quicker than it ever had before, and there's a lot of snowpack left. So there was real concern about we need to manage this existing water that's here, but also plan for additional water coming down. The discharge initially was through the gated spillway, which was the plan and always been used. The emergency spillway had never been used. And initially, they, of course, started watching things carefully, but observed some damage. And when they started observing damage in the principal spillway, they closed the gate a bit, reduced the flows, and moved water up so it would go over the emergency spillway. And actually, they end up going back and forth a bit between spillway flows because they'd see damage in one, move to the other, see damage in the other, and try to minimize the damage that was occurring to both of them. So it was a bit of a real struggle to figure out which spillway to use. They finally got to the point where there was still water coming in. You can see in the photograph on the right here, that the spillway damage occurred. It started to move up gradient. Actually, it tore out the left side of the spillway. And there was concern that it would progress up and actually end up in a full failure of the dam. So they did implement the emergency action plan. You probably heard they evacuated about 160,000 people. You can imagine the distress that caused. It was a progressive failure, as these all are, as we've talked about throughout this. But initially, and that's the photograph in the beginning, the deterioration there at that point, and whether it's caused by cavitation or uplift, my personal opinion, it's both. If you see where that initial erosion occurred or destruction occurred, it's kind of in the points that David was talking about with his cavitation issues. And then, of course, once the channel was broken, once the system was broken, it's talked about you don't have much choice. It's going to do what it wants to do. And water's very good at taking things apart. But just these three photographs show that, that initially started with a little bit of a destruction, but then it just extended it further and further. And then using the emergency spillway, it pretty much washed that downstream portion out. Actually, emergency spillway stayed in place. It wasn't a problem, but the amount of erosion that was occurring downstream of the apron was a big concern because there wasn't a lot of safety factor if that foundation had been removed from each of that emergency spillway. So a couple of things with that is that the discharge was about 4,500 cumecs, which was considerably less than the design discharge for that principal spillway, which I've mentioned was 7,000. And historically, they'd had flows in that spillway much greater than 4,500 cumecs, up to 6,000 cumecs about 10 years or a decade before the incident occurred. So the spillway was in good shape enough, a decade ago, to manage a flow much larger than what I manage now. And so it's sort of like, something's changed with time. And to me, that's a big part of all these dam inspections is aging issues. Anyway, what was found out, I think it was discussed a little bit earlier, that there were some poor design details in the foundation with drainage and cutoff and such. Also in preparation of the spillway, there were poor rock conditions, not good, strong rock that were left in place. And so that ended up that they could have some erosion if there were water underneath there. And also possible movement because you had some long-term settlement with water and everything else that's around that may have provided some offsets for the chute. Also poor preparation that tied in a little bit, and that's actually what that Bozena was talking about was construction is really, really important in these things. And they found in going back through that the construction wasn't done that well, and a lot of inspection was not done very well. And the other part was failure to recognize that the aging impacts on it and how that tied to the design flaws. They did observe changes in operating conditions. And I think there was a photograph that was shown that David showed earlier about the drains carrying a lot of water. Well, at Oroville, the drains did carry water every time the spillway operated. So somebody knew something was going on. And looking at the history of those drains, that flow increased over time with the same spillway flows. So there was I guess, some missed opportunities to make some sense of what was happening as this structure aged. Personally, I think this was not a release of reservoir because it did not release. I think that realistically that the spillway erosion probably would have stopped with time. If you look in the photograph, you see pretty good bedrock underneath that lip. That was the end lip of it, and there was still considerable distance to erode. But when you've got that large of a body of water, you've got to be very, very careful to make sure that you're taking care of issues. One thing about fixing a failure, you become very conservative. You spend a lot of time and money in fixing it. And the other part is that no matter how big your factors of safety are on the repair, there's always going to be a question about what happens if this thing operates again. And not just with the owner, but you think about the downstream people that were evacuated. Every time they get a big significant flow, they're going to think about, ooh, we have a problem again. Anyway, this is just the upper chute. This is what they end up with the emergency spillway, a massive RCC apron that basically was still in water. And one thing about steps and with this system is steps are incredibly valuable at aerating flows. So you just pretty much eliminate cavitation issues with steps on spillways. They actually replaced most of the slabs in the spillway portion, the operating spillway portion that wasn't damaged as well. So a very expensive repair. And what my point on this basically is that they didn't pay adequate attention to the spillway issues over time. The drains were increasing, the concrete was deteriorating, but they didn't really understand what was underneath. They spent $1.6 billion in Canadian dollars to fix that. So that's a lot of money that could have used for something else. Another case study then, this is a reservoir that's an old reservoir again, that's small one. A little dam that's 26 meters high, 500-meter long crest. A spillway that's actually on the right abutment. If you look at this photograph, you can see the spillways on the left side of the photograph. The reservoir, of course, on the upside part of the photograph. And then the spillway runs through a long channel down through basically the right groin of the dam and discharges into stilling basin. It's also the stilling basin for the outlet works. You can see those in the photograph. Spillway components, there's an OG crest, a channel that's a curved channel, as you showed in the previous picture, and then the stilling basin at the basin, and actually below the water level there are dragon's teeth and just a basin to create a hydraulic jump. So very simple, straightforward, that was put in place back in the 1960s. Spillway condition, just a couple of the highlights here that are hard to see in these photographs, but there is a crack in this spillway. And if you note in the photograph on the left, spillway crest, photograph on the left is the left side doesn't have water flowing, the right side does. Something changed. They doubt when they built that, this was built in the 60s, that it was that uneven. So you start getting suspicion of something's going on. And then further down, there is some offsets in the joints. You can see the offset here that's circled in the photograph on the right. So some concerns about that. The big thing, though, that people noticed right away is that this is at the stilling basin at the base of the spillway chute, that there is water right where that arrow point is at the top of that training wall. So there is a lot of uplift pressure beneath that slab. And that's on the left side of the spillway stilling basin. On the right side, where the woman is pointing to, there are these drains, wall drains, and you see the volume of water flowing out of those wall drains. So all of a sudden you start to get a little suspicious. What's that water doing under there? As I mentioned, there are several locations where there are vertical offsets in the joints. You know, as Rosanna talked about, they can be during construction or after construction. There was heave, but it's a little hard to see, but there was heave in the middle of that channel, which was sort of interesting about how there'd be enough pressure to actually lift some of those, those panels up. Interesting, and the concrete was very good shape. Did a lot of cores, and the concrete was just fine. So the concrete collapsed, but some of the other conditions are a problem. They did core the slab and found artesian conditions under the slab. And then, interestingly, the spillway wing walls were a bit out of plumb. So they were starting to move in a little bit. So there was enough pressure that things were deforming a bit with the lateral earth pressures and such. And I mentioned the OG crest was cracked and slopes down to the side. And interesting too, there were longitudinal cracks probably tied into the heave in the middle of the slab that were longitudinal with the spillway channel. So there was enough uplift, and the design for the slab wasn't sufficient to retain that. A couple things in this dam, the seepage areas come and go. That this dam has had problems for many years. The foundation, as was talked about in some previous things, is under drain systems and grout curtains and whatever else are effective. This foundation geologically has some gypsum seams in it, which we know is soluble. So just a lot of things that have occurred on this thing. We do have a pretty good dam safety program here. This project is in Colorado in the US. And that dam safety program kind of oscillated between this dam is not very good to, well, maybe it's acceptable. And then sometimes they've actually more recently said the condition is probably poor and something should be done. So just a lot of issues with this dam relative to its performance, and that ties into the spillway. What's going to happen is that there's been many studies done on this dam over the years, because every time they see a seep or a crack or whatever, somebody looks at it, they do little studies, they evaluate it, maybe do some sort of a simple repair, nothing that really gets to the heart of the problem. What they're doing right now, and this is actually owned by the Colorado Division of Parks and Wildlife, which I think is similar to the Alberta Parks Group, they've gone into looking at, they're going to fix their dams that are dam safety hazards. And so there's a new study that's just being started. That's why I haven't named this dam. But they're going to, look at all the history of what's going on. We're going to do some field investigations and do a finite or a failure mode analysis of the systems that we find, and then develop some alternatives and site selection. The one thing they've done, and I think that sounds like maybe Alberta Parks, you've done the same thing, but Colorado Parks has decided they need to fix their dams. They've got 135 dams and basically reservoirs or lakes that they service around the state. 35 of those are considered high hazard. So, of course, focused on those. But anyway, they're looking at getting funds for the repair, and then they're going to, actually, they're embracing CMGC, bringing the contractor in early and working with them. They've had some degree of success with that. The next one is actually aptly named, I guess, for this presentation, but it is a dam in Colorado. It's a small reservoir that, again, the Colorado Parks and Wildlife works with. It's 7 years old. It's got a kind of a long and checkered history. It's high up in the mountains. It's at 3,000 meters elevation for the crest. Conditions up there are pretty extreme, as you might expect, with very, very cold, lots of snow in the wintertime, and then in the summertime it's can get pretty warm with flows and storms and whatever else there. It's basically, they operate it as a lake, so the reservoir is full all of the time. They don't operate the gates other than exercise it. And so the spillway runs almost all the time, almost all summer long. The spillway operates. Anytime there's inflow, it goes out through the spillway. And so what the issue was that spillway's in poor condition, doesn't have adequate capacity for the flood systems that exist right now. So the initial plan was to go in there and fix this spillway. So the dam itself is small, 12 meters high. It's got a concrete OG crest spillway. It's 6.5 meters long. The drop from the crest to the channel is just a little under a meter. Capacity of it's 27 cumecs, and but the IDF, the incremental or the inflow design flood for the spillway is 108, so way short of the spillway capacity. This is a photograph you see on the right here. The photograph. This is the spillway channel. It's a mass concrete OG with wing walls. The foundation is questionable. On the right side, which is left side in this photograph, that's sitting on bedrock. The left side is soil of unknown depth. Boring showed they go down 6 or 7 meters before bedrock was hit, just under the left side of this. So it's a very steep rock cliff underneath this spillway chute, or excuse me, spillway crest. Also, it's at underseepage. If you note, there's water on both sides of the spillway flowing underneath. And so we don't know what the flow paths are. We don't know what the erosion that occurred may have been because it's on soil. And of course, then what we're concerned about, if the flood occurs, a big flood occurs, we could actually lift this crest up and really do some pretty significant erosion to the point where maybe actually failing the dam itself. Just another couple of photographs that show these the conditions there. This is a downstream, just the water flowing through it. It's a long channel downstream. The photograph on the right, you can see actually the left side is mostly soil and fill. The right side is mostly exposed bedrock. So it's a little confusing there on what would actually happen should we get big flows there. The dam itself is off to the left here. And so if there's a breach in this left, call it a dike or levee, it could go down to the dam, which is a magma dam, to do some erosion damage. While they were there, since they're putting the new spillway in, they thought, well, we got some other problems as well. So they put in a new spillway and channel, which is shown on this the drawing, the plan view drawing. And then because there's some leakage through this system, they put in a upstream blanket and downstream filter and drain in a buttress. And the outlet works was in pretty poor shape. So they went in and relined the outlet works, or put a lining in the outlet works, and then put in a new intake structure. Just some details of what the new spillway looked like. Very standard kind of design with on the upper left is the channel itself. The center part lower is the what the crest is like at the spillway, and then at the downstream end of that spillway chute is shown in the lower right of this photo, this drawing. This is the constructed new spillway. Looking across, being in a wilderness area, you know that the bridge they put across is a couple of timbers from the trees, so make it kind of a more of a rustic look, even though the concrete looks brand new and such. So this is what was put in place. The lower right photograph there shows the channel looking upstream, much more robust than what the soil channel was initially. So this is the upgraded plan for that dam. It's just finished. I don't have a best photograph, but this is with the membrane and the upstream face, the new crest they put in place. One thing you note in this, which you've seen some of, is the riprap is only at the top. And the reason being is that this reservoir is not a reservoir, it's a lake. And they plan to always keep it as a lake. Should the design operation change, if somebody picks it up as a reservoir sometime, they may have to go ahead and put in some additional riprap, but it was a cost-saving method. Anyway, just to close a little bit on case studies. Inspection and monitoring are critical. You know, those are really, really important. And it's not just to look at what you see, but go back into the files and see what's important. And then my opinion is progressive upgrades are priceless. You know, you can let things fester, but they're just going to get worse. And as we've talked about several times, you can put temporary repairs or band-aids on, which help, but you need to look at it very carefully. And it's important too to do a thorough research. This happened on Orville Dam. They didn't do a thorough enough research in their dam safety evaluations to understand the condition under that spillway. And then the other part is expect surprises. You know, the thing that I actually thoroughly enjoy is going back and looking at these upgrades and trying to understand what the original designers and constructors did. One thing in having multiple dams is having some sort of protocol, and of course failure modes analyses are very helpful with that. Doing portfolio failure modes analysis are very important. And then one thing is when you're going to go out there and fix some part of the dam is say, we're going to be there anyway, can we do something else? So that's the end of my presentation.
All right, well, thank you so much to our presenters. We do still have some time for Q&A. I see that a lot of the questions have been answered by our presenters with a written response. So please do take a look in there. And if you do have follow-up questions, we can answer them now. I did see a question about repairs and any discussion around doing concrete repairs at the joints and the effects of that, and if there's any concerns around doing those concrete repairs when it comes to cavitation. I also invite all of our presenters to turn their cameras back on and come back.
Well, I may answer this from Hassan. Can you hear me, I guess? This is with regard to Orville and how they fixed it. Exactly right. What do you do during construction? A couple of things. One is you may have heard that the outlet works was impacted because all of the debris from the erosion of the Pencil Spillway went down and filled the river channel. So they actually backed up water to what is the power plant outlet works. And so that was a real problem. So they had to remove that material, which was, I don't recall, but many tens of thousands of cubic meter of eroded materials that were in that, basically damming up the river. That was one issue. And then they operated it through the outlet works. And the construction was done as about quickly as possible. And then I think there are a lot of hopes that we wouldn't get that big of a snowpack again, but they did lower the reservoir considerably so that they had a lot of room for flood storage during that emergency repair.
All right, thank you. Another question for you, Dan. Can you give examples of Band-Aid repairs? What you referred to there?
You know, this is back to risk assessments. And, you know, the one thing that we've been looking at very, very strongly over the last probably 20 years, is how to evaluate costs and consequence. And so I think that doing these failure modes analyses, even for like repairs like this, are very important. If we say that we've got, as we talked with Bozina talked about, we can do concrete repairs, we can go in and actually see a lot of that instead of going to a spillway slab that's got some cavitation and maybe some offset joints and doing a complete removal, putting in drain systems and replacing it, is to go in and do a selective location repair. But if it's repair, I consider that sort of temporary in most cases, because as I think as Bozina also said too, is we're looking at these projects now to last 100 years. And actually they do last a long time. And I think that's important for us to realize, is that if we're going to do designs for a long period, that we need to take the time frame into consideration. And as in that last repair for the Alberta Park Dam, the preference was to go in and put in a brand new dam, but that was not affordable. They ended up putting a liner in the outlet works, which we said that, it's going to last for 25 years, but it's not going to be lasting for 100 years like the spillway will. And so that was the decision that the owner made, with the understanding, and it was documented all in the designs that were done and in their files, that every next 25 years they may have to go in and do something, because that temporary repair may not sustain for the life of the project. So to me, that's sort of the difference between going in and doing something temporary, which I call Band-Aid, or going in and do something permanent, which is to replace.
Okay, thank you. And I think kind of connected to that now, Bozena, you talked about, or you didn't talk about, there was a question about repairs. I'm going back to this repair thing. And you talked about in the written response, surface repairs are less effective than deeper or full depth repairs. And when I read this, I think a repair is different than that replacement or rehabilitation of that concrete. Maybe you can talk about the difference between those surface repairs and the deeper repairs.
Yes. So I wanted to comment on Band-Aid repairs. When it comes to concrete, they don't work. People do them for a variety of reasons, but they do not work. Now, considering the conditions under which these spillways operate, cavitation issues aside, these are harsh conditions that are also magnified by environmental conditions. I mean, we are in cold climate, we have freezing temperatures, the differential temperatures on top of the slab and below. So we have to be very careful. Now, sometimes what I call a full depth partial repair would work as maybe not permanent, but at least extending service life. So when we think that we can just chip away 25 millimeter or even 40 millimeter of slab and put something on top of that, that may not necessarily work. However, depending on the slab thickness, and that comes with the design that we need to recognize, you can go for a deeper repair that would be way more effective, lasting longer time. But like I mentioned in my written reply, now you have a new piece of concrete that you have to tie into the existing one. Two issues here. If you know that your concrete is, say, 50 MPa strong with the time because it's gaining strength with time, don't try to go with high performance concrete that will have different thermal characteristics. Try to find a concrete mix design that will more or less simulate the original condition, because this is basically 99% of your success of the repair. So that is one. The second one is, now you have a cutout that you partially replaced and put your new concrete in. How do you tie it to the existing concrete? And again, there are different ways, but usually we recommend go with the reinforcing steel, tie it back to the existing one. And then the third one is basically curing. concrete that is not cured properly, and this is mostly wet curing, you can use some admixtures, but that is not always as effective, is going to have a compromised surface. So you add to compromised surface that is not cured properly, potential issues with cavitation, and of course your surface is going to become rough. So, like I said, this is the materials question and should be answered as a materials question. Anything is possible, not a band-aid solution, but a partial repair would extend the service life. I ran some calculations, not necessarily on dams, but on the other structures. And it can be very effective for next 25 to 30 years. And sometimes that's just long enough that the owner needs to make a decision ultimately. Is the design up to the code? Do I have to replace it? Do I have to think about it? But it pushes this decision back by a significant amount of time.
Okay, thank you. So that is, those are, all of the questions have been answered either with a written response or verbally here. If you have any other questions, we've got a couple more minutes here. Or if any of you, I was trying to kind of look through the questions that have been answered. Is there any that you would like to discuss a bit more? That you recall? Oh, we've got another question here. Would a surface repair covering a large high pressure area be more effective than a smaller area?
Not necessarily. This is the judgment call that you take on the surface investigation. Sometimes you engage some coring, but not necessarily.
Okay, so I would like to thank our presenters today. It was a very interesting discussion. I think, yeah, we're getting comments here. Great job. Please join us. What? All right. So we do want your feedback. Please watch out for that email. Join us again. The CDA has 2 webinars coming up, highlighting some of the research from some scholarship winners, CDA scholarship winners. So join us for that. And on the trade show for the 2024 conference, there are 60% of the trade show tables have been claimed. So if you're interested in participating in the trade show, be sure to contact the CDA. And that brings us to a close. So thank you again for joining us. And thank you.